In this video, we'll finish up our discussion of section 4.7 and 8.5 by working with higher order Cauchy-Euler ODEs. There's only a little bit that changed. The method to solve it will be exactly the same. The only thing that's going to change is our cases. Okay, so case one, if they're all real numbers and they are different, I get all these solutions here, and then I can write my general statement that way. It's nothing like if the two numbers were different with only two answers, I would do y1 and y2. Now I just go all the way up. If there are three answers, I have y1, y2, y3. If there are 8 answers, I have y1 through y8. All right, so that's not too hard to extend higher. This one does look different. So these are a repeated real. Yep. So we have this one, and then remember we would take it and add an ln of x. If it's repeated a third time, I do the exact same thing, except for I put a square. So as I go up, if there is if I get 5 equals 5 equals 5, and these are all different roots, right? Like I had something like where m minus 5 to the fourth power. That would tell me that 4 roots are 5. I have 4 repeated roots, right? If this was the case. So what I would write is y1 equals x to the 5th, y2 is x to the 5th ln of x, y to the 3rd is x to the 5th ln of x squared, and then I have a fourth 5, so y to the 4th is x to the 5th ln x to the 3rd. That's how that works. You just keep going up. I like to list them. I don't like to memorize the formula that's there because it's weird because the power, the reason I don't memorize is this power is 1 less than that, and I'll mess that up. Guaranteed I'll mess it up. So what I do is the way I just did it on the screen, I write out my y1, then I add in ln of x, and then I add in the second one for the next one until I finish my list, instead of trying to memorize how many I need. Hopefully that makes sense to you. Then our general solution, we just put all those together with the constants out front, just like any other method. Case 3 was our imaginary case. This one would be our normal case if we just had one set. If we had another, if it repeated, like we had something, let me give you an example here. Take x squared plus 4. Let's solve that. Let me get rid of those parentheses. Right, this is x squared equals negative 4, which tells me that x is the plus or minus square root of negative 4. That is plus or minus 2i. So x is equal to 0 plus or minus 2i. Now, if I had repeated roots like this to the 5th, let's not do the 5th, let's do the 3rd. Let's say that was the case. Then I would have this 3 times, right? 3 repeated. So I would write down, this would be for the first one, this would be for the second one, and then I would do a third one. And all we do here is, if you notice, they add in a ln of x, and then they just add the powers up for that. So it's very similar to a repeated root, except for if it's repeated and it's imaginary, we still have to have the x alpha cosine beta ln of x and the sine one, but we just started adding ln of x's. So we'd have 3 rows of this. So we'd have all the way, if that was my answer for this, I would have 6 y's, right? y1, y2, y3, y4, y5, y6. And the y5 and y6 would look just like these two, except for have a power of 2 in the ln. And then I would do a 3, just like above. All right. Those are good notes to have. That's a good note card thing. That's what I anticipate for note cards to be, is to have these type of things. The more you can memorize it, the better. But the reality of it is, when you guys are working in your fields, if you have to solve DEs, you're going to have methods laid out for you to use. You're not going to have to memorize it. Nobody's going to make you sit in an office and use all of your brain knowledge to help their business. They're not going to want you to do that. They want you to double check your work. So this is the kind of thing I would put on your note card. Okay, so example 4, I have 2 examples of higher order, just to show you how to factor a few of these cases. These 2, I think, factor in the same way. So let's give this a shot. No, they factor differently, thankfully, so I'll give you 2 examples. So notice this is linear. You have to check this. It's equal to 0. That's what we need as well. And then also x to the 3rd, x second, just an x, no x. So this is Cauchy-Euler. All right, so I solve it the same way. These are x's, so it's going to be y x to the m. I'm just going to need through my third derivative now. So y prime is m times x to the m minus 1. Y double prime, I multiply those, I get m squared minus m times x to the m minus 2. And then we need a third derivative, and I'll work this one out. The m squared minus m stays. The m minus 2 comes down. And then I got x m minus 3. I'm going to FOIL this out pretty quickly for us. This is m cubed minus 3m squared plus 2 xm minus 3. All right, so there are all my derivatives. Now I plug it into my DE. This is going to get worse on the next problem, but we need to write small to fit all this in. So x to the third. I'm plugging in triple derivative, so m cubed minus 3m squared plus 2 plus 2m. Almost forgot that. 2m. Right? And then I have x to the m minus 3. That's the first term, plus x squared times the second derivative. So that's m squared minus m, x m minus 2. Minus 2x times my first derivative, which is mx to the m minus 1. And then plus 2 times y. That's just x to the m. All this needs to equal 0. Right? We multiply all this out. We get m cubed minus 3m squared plus 2m. None of that changes. I put my x's together and it gets me an x to the m, like we wanted. Same thing with here. Nothing to distribute, so we just get x to the m. Now that 2 goes to that m, so plus, and I'm going to put negative 2m, so don't miss the negative, x to the m. And then I put 2 in parentheses here, so I don't forget it as well. Equals 0 still. Notice, same thing as the methods in the last video. Even though it's higher order, it still works the same way. There's an x to the m in all of those, so I'm going to factor out x to the m, which gets me m cubed minus 3m squared plus 2m plus m squared minus m minus 2m plus 2 equals 0. So we're going to combine all those. All right, when we combine all these, I'm going to drop the x to the m. Hopefully you can see that at this point. It's my trivial solution, so I can just let it go. And I get m cubed minus 2m squared minus m plus 2 after you combine all your like terms. All right, this one's not clear on how to factor. I'm going to write the term for this. This is factor by grouping. If I have you factor a cubic or a quartic or anything above, that's what's going to work for this. I'm not going to require any other factoring techniques besides factoring a quadratic. Okay, so we get m cubed minus 2m squared. I'm going to group those together. I put my minus here. And then think about I got to change that to a minus to keep my positive 2. Think about distributing that negative back. Right, now I factor. The first set of parentheses has an m squared, so I get an m minus 2. There's nothing in common between m and 2, so I get a 1 minus 2. And then hopefully this is clear what to do next. We get m squared minus 1 times m minus 2. That is factor by grouping. Now I have the zero product property, which tells me that I can set both of these equal to 0. All right, the solutions I get here are m equals plus or minus 1 and a positive 2. Right, that tells me 3 solutions. Y equals x. Was it x in this case? Yep, x to the 1. Y sub 2 is x to the negative 1. And then y sub 3 is x to the 2. That tells me my general solution to this DE is y equals c1x plus c2x to the negative 1 plus c3x to the second. So even though it's a higher order and we had to find some other way of factoring there, it's still solved the exact same way. I will give you things you can manage on your assessments, your exam, meaning I expect you to be able to factor like this. If you need to put an example of this factoring on your note card, then you're going to have to use real estate on your note card for that. I recommend getting that down. That's a great method to know. Gets you out of some tight spots, especially when the math becomes more complicated. All right, I have one more example. This one gets pretty nasty, like long. We're going to fit a bunch. And the reason is we have a fourth derivative. All right, I do need to check linear if it's linear. Fourth derivative, third derivative, second derivative, first derivative, no derivative. Okay, and it's equal to 0. There are no other y's. It is linear. Then I have t to the fourth, t to the third, t to the second, t, no t. So this tells me that this is Cauchy-Euler. So I can make my guess. Y equals it's a t now, t to the m. So y prime is m t to the m minus 1. Y double prime is m squared minus m. Y to the m minus 2. Y, the third derivative, I'm going to go ahead and write this down how it came out earlier. There's no reason to do all the algebra again. I get m squared minus m cubed minus 3m squared plus 2m x to the m minus 3. That's from the last problem. If you want to know how I got that. Okay, now we have to do y to the fourth, though. So that m minus 3 comes down. M minus 3, 3m squared, plus 2m times m minus 3, all x m minus 4. That's the derivative there. Now, we do have to multiply that out. I'm not going to use video time to do that. You just distribute the m all the way through, or the 3. I like doing a box for this. If you need some help on multiplying out polynomials, please let me know. I can send you a video if you need it. No shame. Let's get it fixed now. Okay, so how this works out after I multiply all that out is I get m to the fourth minus 6m to the third plus 11m squared minus 6m, and this is still x m to the 4, minus 4. All right, save us a little time there, multiplying that trinomial by binomial. All right, this is the fun part. We got to write really small because we got to fit all this in here. Okay, so we're going to get t to the fourth times the fourth derivative, so that's m to the fourth minus 6m cubed plus 11m squared minus 6m times x to the m minus 4. That's the first one. That's the biggest one, so we got that out of the way. 6t to the third times our third derivative, which is m cubed minus 3m squared plus 2m times x m minus 3 plus 2 t squared times the second derivative, which is m squared minus m, y to the, I don't know why that's a y there. I don't know what happened there. These were all t's, by the way, as well. See, I do it often. So let's change all these to t's. Forgive me. So used to that x there. So these are all t's, and then we get to go through and fix these two. Thankfully, there's not very many. There we go. T there, and then we have t to the m minus 2, and we're almost done. I'm going to have to put this below. Actually, I can fit this plus 4 times t to the m. And this still equals 0. All right, I am going to skip a step here. I'm going to write t to the m because I know that's going to factor out, and I'm going to distribute any numbers or signs through my m's. So I got m to the fourth minus 6m to the third plus 11m squared minus 6m. That 6 goes through this next part, and I already know I got that t to the m. So I got plus 6m cubed minus 18m squared plus 12m. This 2 goes to both, plus 2m squared minus 2m, and then I have that plus 4 I don't want to forget about. All right, I'm going to combine all these. Make sure you can match this. This is m to the fourth minus 5m squared plus 4 equals 0. All right, it's just a whole lot of algebra. Just be very careful. Right. Unfortunately, this is where we're headed with a lot of these DEs. It's going to be coming next week after this set of lessons. We have a lesson in there, and the problems are super long. I probably will make 2 to 3 videos and cover 2 to 3 problems, and all of it is practically algebra. So work slow. I know you don't want to. I know you want to go fast because I do too. Go slow. Okay, so t to the m is my trivial solution, so I can forget about it. And I take this part and set it equal to 0, right? This does factor to m squared minus 4 times m squared minus 1. You can go ahead and verify that if you'd like. Setting these equal to 0, I got m squared minus 4 equals 0, and I have m squared minus 1 equals 0. This is really nice because I get m equals plus or minus 2, and I get m equals plus or minus 1, which tells me my general solution. I'm just going to go ahead and jump to it. Y equals c1 t to the 2 plus c2 t to the negative 2 plus c3 t to the 1 plus c4 t to the negative 1. Could you put 1 and negative 1 up front with the other c's? Yes, it's all arbitrary. The constants are just numbered to show that they're different. If you like the t to the first being up front because 1 is smaller than 2, that's perfectly fine. All right, so this is this method to solve a Cauchy-Euler. It's a great method. The problem with this method and dealing with it in real life is these equations have to look exactly like they're supposed to look for Cauchy-Euler, which means if they don't, they're useless, and there aren't very many of these things either. So they will every once in a while show up. This whole idea of substitution is the important part from this. This is the part that's actually going to apply to you later, right, in your field. You'll have your own DEs that you're working with if you do at all, and then you will work with these with probably some form of substitution. That's how you'll solve it. So we move forward. We only have a few more lessons of this stuff, and then we get to switch to some new method of solving DEs that I find really fun and very, very weird. We'll get there. Those are called Laplace transforms. We will get there in due time.